Good. So 7. Hello.
My dear.
So we got 7.6 times 10 plus u sine theta plus square root of u sine theta all squared plus 3100. This is where we got to. Please, I hope you can all, those of you who are around can recall. We got to this point, okay? And so 7.666, okay? Now, we are interested in finding an expression for u sine theta, okay? So if we could find a way to eliminate the square root, we can go ahead to finish all that we want to. But if we square this, and then we square this, okay, it will be difficult for us because handling this, okay, it's complex. So we wouldn't square both sides, rather, because we cannot easily simplify what we have here. But rather, what we'll do is that we will send this term, u sine theta, to the other side of the equation. So we have 76 squared minus u sine of theta to be equal to, then this side stands all alone. So we can, effectively simplify. Class, I hope you are with me. I hope you're okay here. So now we square both sides of the equation. Lizzie, what is 76 squared? Lizzie? So each one of you should get ready. You'll be a TA. If I have to. Lizzie, come again.
5776.
5776.
Yes.
Okay, so 5776 minus u sine of theta. Now we are squaring both sides of the equation to eliminate the square root sign. So this side squared, okay, is equal to the square of u sine theta. Sorry, 310. So this side squared. Now it's simpler. Okay, let's expand this. This is 576 squared. 5776 squared plus u sine of theta squared minus 2 times 5776 times u sine theta is equal to the right hand side, and this eliminates the square root. So it's like the roof has been removed. Okay, so we have u sine theta into bracket squared plus 3100. I hope you're okay here. I agree, Adoma Charlotte. What is 5776 squared? Agree,
Mr. Dear.
5776 squared.
The answer is 333 621 76.
Okay. All right. So now you even realize that this side and this side cancels out because this is plus this. Okay.
Please, 76 is part.
Pardon?
It's 333 621 76.
76. Or or what we'll do is that, let me leave it as 76 squared, okay? Let me leave it as this, okay? 5776 squared, okay? Then, please, I hope you agree with me that this and this will cancel each other.
Yes, please.
Good. So, minus, okay, let me take it systematically. 5776 times 2. Adoma, 5776 times 2.
11,552.
Okay, or, you see, this is negative. It will cross the equal sign to be positive so that we bring 3100 to the other side. So it will be 3, this minus 3100, okay, is equal to 2 times 5776 sine of, u sine of theta. I hope it's clear here.
Yes.
All right. So please compute this for me. Equia, square this and subtract 3100 from it. However, let's be sure if what we have within the bracket is either, sorry, hello. This is a plus, please. Originally, what is in the bracket? This is a minus. Check from what I posted on the platform. It's a minus 3100. So please, let's correct that. It's a minus 3100. Okay. Let's check and correct it. So it has to come here to add rather, not to subtract. Please, is that okay? Those are the petty problems in mathematics. If you don't open your eyes, you get it wrong. Okay, so Epia, what did you get? Squaring this and adding 3100 to it.
Please, I got 333.
333.
62176.
62176.
Yes,
Okay,
please.
so divided by 2 by 5776 would give us u sine theta.
Please, the answer is 2,888. 888.
Okay, let me cross check. So this is 10. Okay, 76 times 10. Oh, I think there is an omission. 76. Okay, then we cannot square this side 4. I think I've seen a mistake. This is 76. So now we have 76 is equal to u sine theta plus z. So this has to cross to this side before we square. Please let me correct something. There is a mistake. You see, this is 76. 7.6 times 10, right? Then we have 76 is equal to this plus this. Then we bring this term to the other side. 76 minus u sine theta is equal to this. Before we square, please, when we are doing this, please follow me. I'm also a human being. I can easily make mistake. So when you realize it, you draw my attention. Is that okay? So we have 7/6 minus this. Then we square both sides to eliminate the square root sign. So when we are doing, please open your eyes and do it with me. Where there are mistakes, feel free to draw my attention than ending to later correct it. Class, is that okay?
Yes, please.
Okay, so we have 76 squared minus 2 by 76. And what is 2 times 76 here? Pick one. Lizzie and go, be part. 2 times 76. Oh, the calculator owners.
138.
Come again, 300 and
76 times 2 is 138. 158, so
150. Hey, please point to confirm. 152. Thank you. So 152 u sine theta plus u sine theta all squared. Then we can eliminate the square root sign to have u sine theta all squared minus 3100. Okay, then, and at this point, it's obvious we can eliminate this and this. Okay, so 5, 7, 7, 6. And okay, I'm sure that's the answer for 76 squared. Is that it? Plus 3100 is equal to 152 u sine theta. So are we there? Then u sine theta is equal to, add this to this. 5, 7, 7, 8,
876.
7, 6 divided
Yes.
by 152. And that is equal to
58.39.
58.39 meter per second. So this is u sine theta is equal to uy. Okay, now we were given the time of flight to be equal to 7.6 seconds. And you know range is equal to u cos theta times the time of flight. And you recall that we were given the range, that the tower is 100 and something from 100 and what? Check and tell me. 100 and the tower is okay, 155 meters, sorry, 195 meters away. A projectile is launched from ground level to the top of a tower or of a cliff, which is 195 meters away and 155 meters high. So the range is 195. So 195 is equal to u cos theta times the time of flight, which is 7.6. Therefore, u cos theta is equal to 195 divided by 7.6. So quickly compute that for me. Lizzie, Ayaba, and Co. Adwa, I wish I could mention or learn
25.65.
so u cos theta is equal to 25.65 meter per second. So, okay, so 25.66. Now look at, let's go back to our drawing. We're given a projectile. A projectile is fired from the ground. Okay. So this is and then lands on a cliff. Assuming there's a cliff which looks like a tower. Now, in its trajectory, it has to get to the maximum height, then fall on top of the cliff. Okay. This is the angle of projection theta. And in projectile motion, since a certain velocity is given, okay, at an angle theta, indirectly the velocity divides into two components, ux and uy. The ux component is constant, and that is u cos theta. The uy component is time dependent, okay? But we realize that uy, ux, okay, this is theta, okay, follows Pythagoras theorem. So if we are looking for the velocity of projection, u, the square of it, u squared is equal to ux squared plus uy squared from Pythagoras theorem. So if we know ux and we found uy, you can easily find u. And I want you to do that for me. U therefore will be equal to the square root of ux squared plus uy squared. So once we have ux, which is u cos theta component, and then uy, which is the u sin theta component, please substitute it into this and then help me determine the value of the velocity of projection u. So make me proud. Within, I think this must take you 1 minute. Start work. One minute. Oh. Yeah, are you there?
Yes.
Okay.
Because no more any application.
Exactly.
It's very wrong.
Uh-huh.
What's the application?
And that's what makes physics difficult.
Yes.
Because the mathematical concepts and the physics concept, then
Yes.
application as well.
Yes.
So
Yes.
hello, time is up. Oh. What did we get for u? U is equal to
63.71.
53.71 60.
Yes.
63.
Yes, please.
All right. 63.71 meter per second. Now, the good news is that once you have the velocity of projection, you can also find the angle of projection theta easily. So make me proud. Make me proud in determining the angle of projection theta. This your question, frankly speaking, is loaded. It looks like a simple question, but the mathematical involvement in getting your final answer, it's something. But once you understand it, you are also good to go. What did we get for theta?
66.23 degrees.
60 what? 66.23. That's it. Okay. So with you, you have to substitute whatever we had for ux and uy. But for theta, okay, you can use tan theta. Of course, you know the vertical, which is u sine theta. You know the horizontal, which is u cos theta. So tan theta would give you that. Or you can also use whatever ux is equal to u cos theta, and you have value for u cos theta, which is this. So u cos theta being equal to 25.66, then you have value of u, and so you can easily use that to get theta. Please, I hope it's okay with each one of you, because I want us to quickly finish this question. We discussed the question 2C about inclined plane. So we'll skip that. We looked at question 3, and then 3A. Let's 3 examples of vector quantities and then state the Pythagorean law of vectors. We'll skip it. I think we did that. Then B, I asked you to do it because it's a simple problem. You are given a scale of 1 centimeter to 10. So, and the two forces.
I'm gonna try this on for y'all. It's a fun.
Aresi,
It's a fun adventure
mute
rapid
yourself.
thing. And then I have a source. Is
Hold on.
I might have put this on wrong right now. I think this is then again, I am like a preparing class too, so but it does not accept into my butt. I don't feel like I really the butt like the butt itself.
Mr. Idia, please muted yourself.
Thank you, Nanama. Okay, so 3C. 3C is about the ferryman's journey. The ferryman's journey. Somebody crossing a river. And the question says that a fisherman set off to cross a river 2.5 kilometers wide to attend a meeting. Okay, so let's draw. This is the width of the river. So the lines represent the bank of the river. And we are told that the river is 2.5 meters wide. So 2.5 kilometers wide. Okay. So to attend a meeting, if the river flows due east, so the directional flow of the river, northeast, so the river flows in this direction, due east. If the river flows due east at a velocity of 8.0 kilometers per hour, so let's represent VR of velocity of the river is equal to 8.0 kilometers per hour. So if we are indicating the VR vector is due east, so this is it. And he has 15 minutes to get to the other end of the river. So the time to use in order not to be late is 15 minutes. He has 15 minutes to cross to the other end of the river. In what direction must he head the boat so that he is not late for the meeting? So we are looking for the direction for which the ferryman or the man riding the boat, okay, should move the boat to in order not to be late, because he quickly want to get to the other side of the river. What it also means is that he should look for the least possible displacement. Assuming the ferryman starts his journey from this point. Now, if he takes this displacement and this displacement and this displacement, the possible shortest distance must be from here to this point. Because this is longer, this is also longer. He should ideally, this is how he must go. But the point is also that naturally, because the river is in motion, okay, the boat rides on water. It's a moving water. So if he wants to go here, it is difficult because the river moves. If he wants to go direct, he cannot, because whilst he tries to move direct, okay, the water would also be moving the boat. So eventually, if he wants to come here, he will end up here. And he cannot make that time. Please, I hope you are with me. So our sailors, whenever they are sailing on the sea and they want to come this way, they don't go direct, neither would they go in that diagonal direction. Because if you want to go direct, the river, the water velocity moves the boat, and so you can't come here. If you want to go this way, you end up moving forward. So if you target going straight, that shortest displacement, the practical way to do this is that sail your boat at an angle to your intended displacement. So you have to sail the boat to the shortest, okay, displacement. And as you ride, the water would move and then you will end here. That is the practical way to handle this situation. So the velocity of the boat is in this direction, VB. The velocity of the boat or the man. And then the water velocity is also due east, so it's here. Okay, this part therefore becomes the resultant velocity of the man's velocity and then the river velocity. So this is the resultant velocity of the boat or the man and then the velocity of the river. Please, are you okay? Are you with me? If you have any question here, you can quickly ask so we can continue. Now, so it means that the resultant velocity must be in line with the shortest possible displacement, which would help him make the time. Now, because we know the width of the river, because we know the effective time to use, we can easily calculate the resultant velocity. Okay, so the resultant velocity V is equal to the width of the river D divided by the time. This is giving us 2.5 kilometers. Now, because you are not converting the distance at the displacement or the weight of the into meter, we have to also convert the time to hour. This is in kilometers. This is also in kilometer per hour. So we need to change the time of 15 minutes to hour. Can you do that for me in about 1 minute time? Change 15 minutes to hour, or in terms of hours. I'm waiting. Please, let's be snappy. Leave that in. Okay, so 1/4, which is 0.25. Go, thank you. So T is equal to 0.25 hour. So this is divided by 0.25. This is in kilometer. This is in hour. Therefore, the resultant velocity will be equal to 2.5 times divided by 0.25. I guess that is 10.
Yes, please.
So 10 kilometer per hour is the resultant velocity. Now, once we have the velocity of the moving water and we have the resultant velocity, class, can't we determine the angle through which the boat has to be directed to make the points? So help me determine theta. We have this velocity, we have this velocity. Help me determine theta. Let me check attendance. Okay, I think today's attendance is encouraging. So what did we get for theta? Did you get 30? Sorry, no. It's a familiar value. Yeah, but what did you get for theta?
38.7.
Okay, so if I take tangent, tan of the angle theta, I have opposite, which is VR over adjacent. Adjacent is the resultant velocity. So I have VR is 8 divided by V is 10. So 0.8. So theta is the tan inverse of 0.8. And that is tan inverse of 0.8. That is 50. Yeah, but 50.
It's 38.7.
38.7 degrees. So what it means is that to make the time, the man must direct the boat at an angle of 38.7 degrees from the shortest possible displacement. Or there's another angle, or look at something. The river flows due east. So if this is 38, If this is 38.7, what will be this angle? Class. What will be this angle if this is 38? 90 minus this. Check for me. Yes. If this is 38, what will be this angle? Don't forget, this is 90. This is 90. So if this is 90, this two must sum up to be 90. So this is 52. Okay. If this is 52, what will be this angle? What will be this angle here? If this angle is 52 point something, approximately 52. So if this is approximately 52, Adwa Asante, what will be this angle? Lizzie, what will be that angle? Ekwe Adoma, what will be that angle?
128 degrees.
So 128 degrees. And look at something. The water flows in this direction. So if you take the directional flow, the vector of the water flow, it means that the boat has to be sailed in such a way that it will at any time make an angle of 128 degrees with the directional flow of the water. And this is, so either the boat must be directed at 38.7 degrees from the shortest possible displacement, or 128 degrees to the directional flow of the river. Please, is that okay? So these two angles, obvious. Another question on this, which you would try for me. Please, I'm reading. We have a lot to do, so. Please, I'm reading. Are you ready? I'm told I'm rushing the class, but it's because I want us to do a lot within a time. I think this will be there for you to write. So,
Yes.
okay. A boatman can row with a speed of 10 kilometers per hour in water. A boatman can row with a speed of 10 kilometers per hour in water. If the river flows at 5 kilometers per hour, in which direction, if the river flows at 5 kilometers per hour, in which direction should the boatman row? In which direction should the boatman row in order to reach a point? In order to reach a point on the other bank, directly opposite to the point. In which direction should the boatman row in order to reach a point on the other bank, directly opposite to the point from where he started? to reach a point on the other bank directly opposite to the point from where he started in the shortest possible time. In the shortest possible time. Now, if the width of the river is 1 kilometer, if the width of the river is 1 kilometer, find the time taken to cross the river. If the width of the river is 1 kilometer, find the time taken to cross the river. This is a question similar to what we've just discussed, okay? So you apply the solution of this to solving the same problem. Question 4. What is a force? We will jump. Explain the following and list 2 examples each. Contact force and field force. We will jump this one too because you can determine it at any time. So we can look at the calculation. All right. So check, or I'll send you the marking scheme so you can refer to these ones. Today, I want us to finish and then look at moments. The next question, 4B. A body of mass 100 kilogram. A body of mass 100 kilogram is placed on a rough horizontal floor. If the body is moved at a constant speed, by the application of a horizontal force of 500 Newton, calculate I, the normal reaction on the body. I, the coefficient of friction. All right. It is always easier when you put the question or the information given into drawing. When you draw, it helps you understand better. So we are told that a body of mass is placed on a rough horizontal floor. So anything to represent horizontal floor. Once it is rough, then all that it implies is that there is consideration for friction. If there is no consideration for friction, the statement will be a smooth or frictionless surface. But once it is rough, then there is a frictional interest. So this is the mass of 100 kilogram. Obviously, its weight, the weight of a body always follows the direction of gravity. Gravity is always perpendicular to the horizontal floor or the ground. So its weight vector will be downwards W. Now, once this is a body that lies flat on the surface of the earth, okay, Newton's third law, forces move in pairs. There will be an equal magnitude force, but oppositely directed to the weight vector, which we call as the reaction, the normal reactional force. When a body lies flat on the ground, the reactional force is equal to the weight, which is given by the mass of the body times acceleration due to gravity. So that answers the normal reactional question. Now this mass is being pushed by a force, a horizontal force of 500 Newton. Okay. Now once the statement or the details from the question says that it is a rough horizontal surface, then there is an opposition, which is frictional force. Frictional force always opposes the relative motion between two bodies. So if this box is being pushed due east, friction would oppose it due west. So friction is here. Once there is a statement that if the body is moved at a constant speed, very, very important. We are told the body is moved at a constant speed. If a body is moved at a constant speed, then class, what do you think will be the acceleration? If a body is moving at a constant speed, what will you say about the acceleration?
0 meters per second.
So acceleration is 0. When acceleration is 0, then it means that the net force acting on the body is equal to 0. Because Newton's first law, okay, if the net force says that if the net force acting on a body is equal to 0, two things. Either the body stays stationary if there's no external force or resultant force or a net force acting on a body, two things. Either the body remains at rest, stationary, or the body moves with a constant velocity in a direction, in one particular direction. So once the velocity or the speed is constant, it means that acceleration is 0. If acceleration is 0, it means that the resultant force or the net force acting on the body is 0. Therefore, what it simply means is that if speed is constant, then it means the force here and the opposition force or the opposing force balances. And so they are resultant or the net is equal to 0. This must be equal to this for the body to move at a constant speed. Okay, so for body to move at a constant speed, it implies that the resultant force acting on the body is 0. And if the resultant force is 0, simply it means that the horizontal force must be equal to the frictional force. So that when you add the forces in both directions, it will sum up to 0. Then we have what we call a condition of dynamic equilibrium. We will look at Newton's laws and you understand the terms I'm using very well, okay? So this is the condition for us to obtain this constant speed thing. So if frictional force must be equal to the horizontal force, then we equate this 500 Newton to frictional force. Friction is given by the coefficient of static friction which is a measure of the nature of the surface, times the normal reactional force. So F is equal to mu R. So if F is equal to mu R, for a body, please, for a body that lies horizontally on a floor. Because when it's on an inclined plane, it will change. So we have found R. R is equal to the weight, mg. So it means that 500 is equal to mu times the mass, which is 100 times gravity. Gravity, let me check if the question gave us a value. If we are not given, then we use 10 meter per second. Yes, we are given G to be 10 meter per second square. So 10. So we can easily find the coefficient of friction, static friction. Please help me get that. Help me obtain mu. 0.05. Okay. 1, 2, 1, 2. So this is 0.5. Coefficient of static friction is unitless. It's a non-dimensionless constant. So this is it. As for the second question, we've answered it. The normal reaction is equal to the weight. And so it's equal to 100 by 10, which is 1,000 Newton. So this is a simple question on forces. Going forward, I'll give you questions that are a bit of a tougher expectation than this one. Any question? Class, any question?
No, please.
Okay. All right. The last question. State the principle of movement. Priscilla, state the principle of movement. Priscilla, this question is for you.
Ish. Mr. Adrian, please, I'm just trying.
Okay, try.
When a body is in constant velocity or equilibrium, the sum of the anti-clockwise moment is equal to the sum of the clockwise moment.
That's one. Thank you. Okay. What's the second principle? So the first principle says that to obtain equilibrium, you see, the two principles all dwells on equilibrium states, where the net turning effect acting on the body is 0. So the first one is that the sum of the clockwise moments must always be equal to the sum of the anti-clockwise moment, or the net turning effect on the system must be equal to 0. What is the second principle of moment? Yes. What is the second principle of moment? Yaba? Yaba? Yaba, are you there? Okay, let me call somebody else. Lynn. Lynn, the second principle of moment. Okay. The next principle is that, by the way, did you do moment?
No,
Did you?
please.
So please.
Oh, okay. Then I think let's use this opportunity to begin moment. Okay. Let's use the opportunity to start moment. All right. What is moment? Moment of a force. Okay. What is moment of a force? When we talk about moment of a force,
Okay.
we are talking about the turning effect produced by a force. So moment is defined as the turning effect. The turning effect produced by a force. Around an axis of rotation. Around an axis of rotation. Okay. This is so practical. It is so practical. You see, when you are entering into your room, one, there is the doorknob. The doorknob, if I'm to sketch anything, looks like something like this. If this is the handle, okay, connects to the wooden frame through something. And this is a point around which turning takes place. This we are calling as the axis of rotation, which in JHS you were calling as the pivot or the fulcrum. Okay, so turning actually takes place around this. So to open the door, what you do is that you hold this and then turn through a direction. Okay, how do you turn it? You apply a force. A force, this is a downward force. And the application of the force causes this to turn. This is moment. Okay, so the application of the force causes the door to the doorknob or handle to turn. So you apply a force, okay, and the force applied causes a turning effect of the handle. The same door frame you have, this is the door, the main door. Then this door is connected to the wooden frame through hinges. So these are the hinges connected to the wooden frame. So if you want to open the door, you apply a force in either backward or forward direction. Okay, and the door turns around the hinges. Application of movement. Okay, when you are opening your Coke bottle, okay, removing it, you apply the opener and then apply a force, okay, through a upward direction, turning effect produced by a force. So there are lots of application of movement. So when we talk about movement of a force, we are only talking about the turning effect produced by a force around an axis of rotation or around a pivot. Class, are we okay? Are we okay?
Yes.
So we can actually talk about a lot of applications of movements, okay, where there is a turning effect. Now, how do we determine measure? This is the definition. How do we measure movement? Okay, Amma, your hand is up. Amma, go ahead and ask.
Please. So the lawn spray in the lawn spray in gardens, is it an example of an application of movement?
The what?
The lawn spray, the one that watered the garden, it turns its hands upwards like the where the water produced from.
Yes, I get you. But you see, here, what is the force? The force which causes the rotation of it is an electrical force. We are looking at here, we are talking about mechanical one, where a visible force by somebody or something is applied to cause a rotation. Is that okay? What you are talking about, yes, the sprinkler is also a rotation, but the force is as a result of the electric field created. All right. Okay. So the moment of a force is determined by the product of the force, is determined by or is measured by the product of the force, is measured by the products of the force and the perpendicular distance. Perpendicular distance from the axis of rotation. So let me give a drawing. This is a bar. When we were kids, we used to play the seesaw game, where there's a bar, uniform bar, and we support it at a point, usually the center. So we pivot it. Then Ekuyadoma sits here. Hey, I don't, maybe she's standing rather. And then Amma also sits here. Okay, now turning effect occurs around this. So this is the axis of rotation or the pivot. The axis, this is the point around which turning takes place. Now, Ekuyadoma exerts a force in this direction. Amma also exerts a force in this direction. What happens is that, what do you think would happen if Ekuya and Amma, okay, both have the same weight? When their weights are the same, what happens? Yes. If their weights are the same, what happens?
It will remain the same.
Come again. Lizzie, come again.
There will be no movement.
There will be no movement. So there will be, this bar will be stable. Either we say it will be stable or will be in equilibrium. Equilibrium. Okay, so there wouldn't be any movement. It would just be flat, level. Now, should we add Lizzie? If Lizzie comes to join Ekuyadoma, then there's a tilt. A tilt. Okay, Amma is raised. Here, there has been a turning effect there is turning in the clockwise direction. Okay, Amma goes, yes, Amma also follows it. Is that okay? So this is a classical example of turning effect produced by a force. And so we can determine moments by the product of the force. So the force produced F by, you see, in moment, it is always important that we measure the perpendicular distance from the line of action of the force to the point around which rotation takes place, the axis of rotation. Okay, so the perpendicular distance from the force to where the point where rotation takes place. Assuming this is A, then it means the turning effect or the moment produced by this is equal to F times A. So moment is determined by the product of the force and the perpendicular distance from the point around which rotation takes place. Class, are you okay?
No, please.
Okay. Now, moment is a vector quantity. Moment is a vector quantity. Okay, meaning it has both magnitude and direction. It has both magnitude and direction. So if moment can be calculated by multiplying force by the perpendicular distance, I want you to help me to determine the units. What do you think it will be the unit of moment?
Mr. Yeah.
Amma.
Please, what have you written for A?
Oh, this symbol only represents a perpendicular sign, perpendicular distance. Okay. What's the unit?
Newton per meter.
No, look at it again. Force times
Newton
perpendicular. Good. L. Let me change A to L. Else you may confuse yourself with area. So the SI unit of moment is Newton meter. Starting as M. Okay. So that's meaning what it means is that, let me create something. I have this doorknob. It rotates around this point. This is the axis of rotation. Okay, O. Now, three forces are exerted on the handle. Force A, force B, and force C. If I want to determine the turning effect produced by A, B, C, which one will be greater, which one will be lesser, and why? Yes, which of the three forces will produce the largest turning effect and why? Please, if you are ready, you can raise up your hand. Lizzie?
The force A would give a greater turning point because
Why?
Because the force and then the distance. Okay, no, the distance from the turning point to the force.
Mhm.
Well,
Okay.
yeah.
Lizzie, I understand your answer. So let's look at this is the line of action of A. The line of action is an extension of the direction of the force. Then let's look at the distance. The distance from the force A to the axis of rotation. And the distance must be perpendicular to the force. So this is the distance, same distance L, or maybe let's call LA. Is LA perpendicular to the force? Is LA perpendicular to the force?
Yes. Yes,
So,
please.
so look at the distance. This is the distance from here, from the axis of rotation O to where the force acts. And we can create that perpendicular relationship. Yes. So if we are to calculate for the moment or turning effects, moment of A, okay, would be equal to the force A times LA. Now, yes, Lizzie's answer is true because this length from where the force is to where the axis of rotation is greater than all of them. Here, the assumption is that, okay, force A is equal to B and is equal to C. So we have the same magnitudes of forces, but because of the distance, this will produce a greater turning effect. Now, which one would produce the lesser turning effect? Which of these two would produce the smaller, okay, turning effect, and why? Yes. Hey, Lizzie, let somebody else come in. Yes. Lizzie, let somebody else come in. Or I should call. Equia Doma.
Yes, please.
Equia.
Yes.
Which of the forces would produce the lesser turning effect?
C.
Why?
Because it's not perpendicular to the distance.
If you want to see whether it is perpendicular, draw the line of action of the force. When you draw it, this is it. Okay, then measure the distance from the point of axis of rotation to where the force is. This is it. And so you can see that perpendicular turn. So it means the distance from where the system rotates to the force, they have that perpendicular relationship. But this would give us the smaller turning effect because the distance from the point of rotation is smaller, implying that moment, which depends on the force and the perpendicular distance, moment is directly proportional to the force. The same moment is directly proportional to the perpendicular distance L. So when any of these two increases, it will also increase moment. Class, are we okay? Are you okay?
Yes, please.
That is why when you cannot hold a smaller part of your door handle to turn it, yeah, you want to enter your room, and then when you are going in, instead of you to hold the end and then turn, you decided to hold this small part and then turn. It will never be easy because this would give you a lesser turning effect moment. Because if this is the axis of rotation and the force is applied here, because the distance is lesser, it will give you a smaller moment. I hope you're okay.
Yes, please.
Okay. Let's talk
Yes,
about
please.
couple. A couple. A couple. This is not the couple we know, but couple and the moment. Couple. Yes, I want somebody to. Yes, so I know you are a gay student, you read a lot. Maybe you have come across what a couple is. What is a couple? Inshira, yes, the two Inshira, Princessa, okay, Alvina.
So
Alvina.
please, a couple is a two equal but opposite force applied parallel to each other.
Thank you. Yes, I told you so. Please, if you have a different view, you can also share with that about couple. What is a couple system? Okay. And the moment, whenever you have two, as Alvina said, whenever you have two forces chosen in such a way that they have the same magnitude, but they are directly opposite to one another, acting at different line of different along different lines. Let me. So this is a common line. Now we have two forces acting in opposite directions. So we have this force acting upward, F1. Then we have another force acting downwards, F2, F2. Now, in terms of magnitude, you see, this force is perpendicular to the common line of action. This is also perpendicular to the common line. Now, in terms of magnitude, F1 is equal to F2. So all that we are saying is that the two forces have the same magnitude, but their direction is opposite, separated by this distance L. So from this point to this point is L. This creates what we call a couple system. Okay, so a couple system is formed when two forces of the same magnitude, okay, but oppositely directed, okay, are perpendicularly from a common line of action. It creates what we call a couple system. Okay, so a couple system is formed when two forces equal forces
No, I just went there.
when two equal forces act oppositely to one another at a common line of action and separated by a distance. The turning effect produced by a couple. The turning effect produced by a couple. This turning effect thing, you see, in our local books, we call the turning effect produced by a couple as the torque. Whereas in foreign books, the turning effect produced by a couple is said to be the moment of a couple. The moment of a couple. We call it as torque. They indicate that as the moment of a couple. In foreign books, torque refers to moment. So they refer to the turning effect produced by a force as torque. Okay. So in the local books, this is what you see as what we call as a turning effect produced by a couple system. But in some foreign books, the moment of a force, the turning effect of a couple is called the moment of a couple. Torque is used as a turning effect produced by a force, which is the same as moment. Okay. Now, let's see some of the applications of a couple system. Some applications of the couple system. Yes. Look around and then try to identify a situation where two forces of the same magnitude but oppositely directed, okay, is applied in our homes, industries, schools, communities, and so on and so forth. Where something you can relate to a couple system. Yaba, relate one. Yaba, help me relate one. Eresi. Hey, Yaba, you are quiet. Oh. Eresi, help me relate a couple system. If you are ready, you can just look around. Try to identify a situation where you have two forces of equal magnitude. Okay, Akuya, Akosia Adomajima.
Mr. D, I don't know if it's correct, but I see the bicycle wheels.
Exactly. Exactly. The only pedaling of bicycle. Yes, it creates a couple system. Look at it. One force, one of the legs pushes this way, okay, whereas the other pushes in the opposite. So while this goes this way, the other goes backward, okay? In riding a bicycle, that's how it is. So riding a bicycle or pedaling a bicycle. Instead of riding, let's use pedaling a bicycle.
Sir,
Hello.
please, can you say turning a key in a lock?
Yes, exactly. Exactly. Okay. Once you turn this way, the other one pushes. Okay. Turning the key in a knob. Yes.
Opening and closing the tap.
Yes. Opening and closing the tap. Yes. Opening and are you really looking around or you are reading from the book? You have to be touring. Your
Sir,
your mind must be touring to get it. Yes.
sir, please, I wanted to ask, like, maybe, like, you see, when you're driving, the steering wheel,
Exactly. Steering a wheel. Steering a wheel. Okay. So this one goes here and then the other one goes the oppositely. So steering a wheel, yes. But the question is your mind, the brain taking a tour, or you are reading from the closest book?
We said you asked about whirlwind.
Pardon?
A whirlwind.
Oh, I can't hear you.
Whirlwind.
Whirlwind. Whirlwind. Whirlwind. As for whirlwind, hey, I'm trying to figure out the distance, the perpendicular distance between the two wind forces. It looks like it, but honestly, because we cannot identify the that perpendicular distance to the two forces, it's difficult to accept, right? I think you've mentioned quite a lot. So if you have a situation like this, determining the turning effect of the couple is the product of, so the turning effect, which the torque will be equal to, since the forces have the same magnitude, is the product of one of the forces times the perpendicular distance between them, L. Now, if it happens that there is an axis of rotation between the two forces, and then an example is the steering a wheel. You know, in steering a wheel, there's something, a metallic something which holds that circular thing to the wheel, to the four wheels. So the turning takes place around that thing from the steer to the tire rod. So if there is an axis of rotation, and this is L, then this will be D on 2. This will also be so this will also be L on 2. This will also be L on 2. In this case, the turning effect, which is the torque, can be calculated by F, one of them by that length, L on 2. Please, are we okay?
Yes.
Are we okay? All right. So let's go into how to calculate this turning effect moment. Now, we just saw that if you have a rigid bar pivoted at one end, to calculate the torque, maybe this is the force F1. The distance from the axis of rotation where turning is to the force is A. If this is another force, F2, the distance from the pivot to where the line of action of the force is B. So if I'm to determine the turning effect produced by F1 and F2, the moment by F2 would be equal to the product of the force and the perpendicular distance from the pivot. So here, moment produced by F2 would be equal to F2 by B, and moment by F1 is equal to F1 by the perpendicular distance from the axis of rotation or the point of rotation. Is that okay? So, example, if this is 5 centimeter, and then this is also another maybe 4, and this force is maybe 5 Newton. This is also 6 Newton. Then it means that the moment produced by F2 is equal to 5 Newton times 5 centimeter, which is equal to 25 Newton centimeter. Maybe some of you are admirers of SI units, so you want to change to SI units. So in this case, the turning effect produced by F2 becomes 5 Newton times 5/100, but in meter. Okay, so this becomes 25 on 100, which is equal to 0.25 Newton meter. Please, are we okay? Are we okay? What about the turning effect produced by F1? Calculate that for me. Moment by F1. Calculate the moment by F1 in Newton centimeter and then Newton meter for me. Are we through?
Yes.
Uh-huh.
Yes.
Okay. Okay. Let me do it so you can use that to mark. So the moment turning effect produced by this will be 6/4, giving us 24 Newton centimeter, which is the same as 24 divided by 100. So 0.012, 0.24 Newton meter. So that's how to calculate for moment or the turning effect produced by forces. Now, sometimes the force may not be directly perpendicular to the distance from the axis, the distance from the point of rotation. And this is it. We may have a situation like this. A force F1 acts here, and the angle it makes with the bar is theta. We can have this situation and then be asked to indicate the turning effect produced by the force when the distance from where the force acts to the point of axis of rotation is L. If you have a situation like this, how would you calculate the turning effect produced by the force? Any idea? If you have any idea, you can share with us. If you have any idea. So Here, yes. Okay, Alvina.
Sir, please, the force times distance cos theta.
The force times distance cos theta. Alvina, can you explain?
Sir, so if, let's say, if the downward force applied on the body of length, that will be the,
On the bar.
yes.
Okay, any different view from what Alvina told us before I come in? Okay, let me come in. You see, we are defining moments as the product of the force and the perpendicular distance. The distance from where the force acts from the axis of rotation must be perpendicular. Okay, so once this force acts at an angle theta to the bar, to get the turning effect, we must resolve the force to get a component of this force which is perpendicular to the bar. So it's like we have this as the horizontal. The force acts at an angle theta. This is F. Once this force acts at an angle theta, we need to resolve the force to get a component of it which will be perpendicular to this bar. This is the bar. The length is L. We need to resolve F to get a component of the force which will be perpendicular. Now, if we extend this line, not extend, but if we create something, if this is theta, we can get the corresponding angle here to be 180 minus theta. Please, is that okay? Let me draw here.
Yes.
Let me bring this here. This is the pivot. The pivot is here. Okay. The bar has a length L. The force, this force acts through an angle theta. This is F1. We are interested in getting a component of this force which will be perpendicular to this. So when we extrapolate this, not as in increasing the length, we can create an angle alpha. Alpha we know is equal to 180 minus theta, we know. Now, we are interested in getting a vertical component of this force. We've done vectors, so we are not interested in the horizontal component. We are interested in the component of F, which will be perpendicular to this. And what would this side be? Yes, you've done vectors, so help me get the component of F1, which will be perpendicular to the bar. Yes. Yes.
5.
Lizzie, come again.
5 Newton.
No, this is, I'm giving you letters, so this is F1. F1. Okay, the angle is alpha. What will be a component of F1 which will be perpendicular to this?
Distance. D.
Oh, vectors. Okay.
F1 sine alpha.
Exactly. So this side, which will be perpendicular to the bar, okay, when we resolve it, the angle is alpha. So when you take sine of alpha, sine alpha is equal to opposite, which you don't know, divided by the hypotenuse, which is F1. Okay, therefore, the vertical component which we are looking for will be equal to F1 sine alpha. So this part is equal to F1 sine alpha. Okay, by equal vectors, instead of having this here, we can bring it here because vectors are equal when they have the same magnitude, direction, and are parallel. So by bringing this here, we've had a component of this which is perpendicular to the length, and so we can determine the turning effect. The moment or the turning effect, therefore, the moment therefore will be equal to, we are saying is the force. The force is, which is perpendicular to the bar, is F1 sine of alpha, and then the distance is L. So we have F1 L sine alpha. Okay, now, because sine of theta is equal to the sine of 180 minus theta. Okay, so look at something. If this is theta, the corresponding angle is 180 minus theta. Okay, what I'm saying is that assuming this is 120, theta is 120, we have sine 120 would give you the same value as sine 180 minus 120, which is sine what? 60. Okay. Sine 120 is equal to sine 60. Sine 150 is equal to sine 30. So all that I'm saying is that if you are given, this is an obtuse angle, 120 or 150, there's no need of you to subtract this from 180 to get the acute angle, because what the obtuse angle can do, the acute angle can do the same thing. So if you give me a force F1 acting at an angle of maybe 120 to a length, then the moment would be, we just saw that it is F1 times the length times the sine of the angle. So, okay, let me put a question. The question would clarify what I'm saying better. So, assuming we have a force of this, F1 is 60 Newton. It acts at an angle of 150 degree, 150 degree to the length, the length from the pivot to where the force acts. This is 5 meters. By what we've just calculated, we realize that the moment when there's an angle is equal to the force times the length times the sine of the angle here. What do you think will be this angle? What do you think will be this angle?
30 degrees.
Good, 30. So if I'm to calculate this, this is equal to 60 by 5 by sine 30. This is 60 by 5, sine 30 is half. And so 3. Okay. So this is 15.0 Newton meter. Now, so this is the turning effect produced by this. Now, because sine 30 is equal to sine of 180 minus 30, it means this is sine 150. Okay, it means that I can put this angle direct here without subtracting 150 from 80 to get this, and it will give me the same value. So use sine 150. Whenever you are given an angle theta, use the angle and you get the same answer. So 60 times the length times sine of 150 will give you the same results. That's what I'm saying. Hello. Good afternoon.
Miss Adia, please, you are muted.
Hello. I'm asking if you are okay with the explanation.
Yes, please.
So all that I'm saying is that if you are given an obtuse angle, whatever angle you are given, okay, you need not to subtract it to get it. Just use it and the value is the same. All right. So a quick example. A quick example. I have this force of magnitude. The magnitude of the force is 100. The length is 6 meters. This is 100 Newton. It acts at an angle of 45 degrees to the bar. Calculate the turning effect produced. Calculate the turning effect produced by this force. Yes. I think 1 minute. Just within 1 minute. Are we through? Are we through? So when you resolve it, okay, you get this component 100 sine 45 acting here. 100 sine 45. will be a component of this force which is perpendicular to the bar. Okay. Now, though the force acts in this direction, but it is this component, perpendicular component, which will turn the bar in that clockwise direction. So the moment produced by this, which is equal to the force times the perpendicular distance, L, the component of the force which is perpendicular to the bar is 100 sine 45 degrees. Then what is the length? The length is times 6 meters. Therefore, sine 45 is equal to √2/2 times 6. So we have 300 √2. Okay, which is the same as 3 times 14, 1 point. √2 is 1.414. 1.414. So 1, 2. Okay, 3 times 141.4. Which is equal to, what is 3 times 141.4? Quick one.
424.6.
4.
424.6.
Just multiply this by this. Let's confirm if that's the correct answer.
Yes, please.
I think 424.2.
Okay, so
What?
that is it.
4.26, sorry.
Okay, don't worry. Okay, so that is it when the force isn't directly perpendicular. Tomorrow, what we'll do is I'll give you a number of forces acting along the bar, some perpendicular, others not perpendicular, so that we look for the resultant torque or moment. Is that okay? So we'll end it here. As for moment, we'll go into it deeper so that when you see questions, you can easily walk through it. So this is where I draw the curtains on our today's meeting. Yes, thanks for, being part of the show. And please, when I give you work, I gave you a Sunday challenge. And unfortunately, I've had only a single response. Okay, the question I put there isn't difficult. So try it and then let me have the feedback. Until I think same time tomorrow. In fact, take care of yourselves, read, and then, submit your work. Bye-bye. All right.